Okay, so today we're going to be covering precision versus accuracy as well as scientific notation. So, accuracy is basically how close the results are to the true or expected value. So, what that means is like, let's say in a lab you were expected to get 30 grams of sulfur by doing a reaction. Let's say you only obtain 10 grams of sulfur instead. So, pretty much only 33% yield. As a result, your results are not accurate because you were supposed to get 30, but you only got 10. So it kind of deviates from there. Precision, on the other hand, is how closely your results relate to one another. In other words, how close the data points are in relation to one another. So what that means is, let's say you run this experiment multiple times and you obtain 10, 11, and 10 grams of sulfur each trial. So one trial you got 10 grams, another you got 11 grams, and then you got 11 grams again, or 10, sorry. Since you're consistently getting around the same value of sulfur, like you can see how 10 and 11, like all those numbers stay pretty close to one another. Um, they're closely related, therefore you are getting precise yields. So you're consistently getting around the same values and it doesn't deviate too much. So in order to clarify this a bit more, let me go ahead and draw here. So let's go ahead and look at this first target here. Um, let's say one time we shoot here, one time we shoot here, and one time we shoot here. Would you say that this target is accurate, precise, or neither, or both? In this case, since everything is widespread, so in other words, they're not clumped together in one specific area, it's not precise. And also, it's not accurate because none of them actually ever hit the target itself. So none of them got the expected value, which of course is the bullseye when you're aiming for a target. On the other hand, let's go ahead and look at the middle target. Let's say I got this here. We can see how the points are relatively clustered together very nicely, so we know that this is precise. However, it's still not accurate because we're not getting the bullseye being the expected value. Now, if we go over here and we say we did this is both accurate and precise because close to the expected value, it hit the target, and also the data is very well condensed, so it doesn't deviate too far. Now let's do some scientific notation. So scientific notation is the representation of numbers in the ones place that have trailing decimals to a certain power of 10. So generally, when we're doing scientific notation, it's often used to represent very large numbers that we're dealing with in chemistry. And one in specific that you will be using momentarily is Avogadro's number, which is a massive number to the power of 23. So it has 23 trailing zeros on top of, I'm sorry, that's wrong. It has 23 placements, you know how there's like ones, tens, hundreds. It has 23 of those basically. The benefit of using scientific notation is that there is no ambiguity in significant figures. So when you're just looking at something that's written in scientific notation, you can just literally count the left-hand side, and then that will be the correct number of significant figures. So like, for example, let's say I have 2.01 times 10 to the third, let's say kilograms. And we just have to count, oh, look, there's 1, 2, 3 significant figures. So it's really straightforward with the number of significant figures that you're using when you're doing scientific notation. And then when we're multiplying and dividing exponents with the power of 10, so that means like this right side factor right here, when we multiply them together, we add the exponents together. And when we divide, we subtract the exponents together. So what does that look like? So let's say we have 10 to the power of 3 times 10 to the second. What that will look like is 10 to the third plus 2. And when we add that, 10 to the fifth. So we add the exponents together when we're multiplying the powers of 10. And then let's say we're dividing them now. So we got 10 to the power of 3 divided by 10 to the power of 5. So now we're going to subtract them instead. So we would do 10, 3 minus 5, 10 to the negative 2. And that's when we would subtract the exponents together. So let's do some practice problems here. So write the following numbers in scientific notation to the correct number of significant figures. So in this first example, we have 2004.13, and we need to convert that to 3 significant figures and convert it to scientific notation. So we know that when we're writing scientific notation, it has to be in the ones place first of all. So that we're going to go ahead and put a 2 and a decimal right off the bat because it must be in the ones place. And then it's asking up to 3 significant figures. So we're going to start adding significant figures until we reach 3. So this 0 is significant, that's 1. And this 0 is significant, that's 2. So we'll leave it as that. So that on this side, we have a total of 3 significant figures. The 2, the 0, and the 0. Times 10, we got to see how many spaces the decimal place moved over. And we can see that it moved, let's see, 1, 2, 3 to the left. So we're going to have an exponent of 3. And the reason why it is positive is because if you think about it, we're taking this smaller number and multiplying it by a big factor of 10 in order to create that big number that we were talking about, which is 2004. So of course we would need to multiply it by an exponent that's positive as opposed to negative. Here we have a very small number that we got to convert into scientific notation and to the correct number of sig figs. So we're going to do the same thing we did before. So we take the first number, which is 1 right here, and we're going to put it in the ones place and then in a decimal right after. And then it says it wants it up to 2 significant figures, so we're only going to add 9 times 10. And this is where things get confusing because a lot of students get confused as to why the exponent is negative. But as you can see, we're starting off with the decimal place here, but we need to move it backwards in order to make this number into the ones place. So let's find out how much we need to do it by. So 1, 2, 3, 4, 5. 10 to the negative 5. And of course it's negative because we're going from this number, which is bigger than this decimal over here, right? So of course we need to multiply it by an exponent that's going to be negative because it should be smaller when we're representing it in scientific notation. Now let's take this big number here. It wants us to round it to 3 significant figures, so we do our first number, 1.20, right? There's 3 sig figs here. And then we just got to count how many spaces the decimal place moved. So 1, 2, 3, 4, 5, 6. Right, I did that right. 1, 2, 5, 6. So 10 to the 6. And then this is in scientific notation. And for this last one, this one can be a lot trickier for students, but the idea here is that this is basically just a number. It's not in scientific notation because we know that in scientific notation, it would be in the ones place like everything else that we wrote up here. But this is not, this is in the hundreds place. So we need to move the decimal 1, 2. But we also have to keep in account for this 10 to the second power up here. So let's write it first to 4 significant figures so we don't confuse ourselves. So 1.032. That's 4 sig figs. And then we have 10. Okay, so based off of this little diagram here, we move the decimal place 2 places for the number on the left right here. So there's 2 for sure. And we also have the fact that it's being multiplied by 100. So that's 10 to the second power. So we're going to add 2 here, which will give us 1.032 times 10 to the 4th power. So you can see how adding the exponents becomes crucial when you have complex numbers like this. So I took the fact that we moved the decimal place to the left 2 right here. And then I also took into account that this number was being multiplied by 100 here. And then I added those 2 together, and that's how I got 10 to the power of 4. All right, and that's it for significant figures and accuracy and precision.